The universe became transparent. Then it disappeared. To human eyes, transparency means there must be something to see. I treat it differently, as a clear path for light, even when no source exists to illuminate that path. This difference opens the cosmic dark ages. About 380,000 years after the Big Bang, the optical barrier of the primordial plasma gave way. Until then, free electrons scattered photons so frequently that light could not preserve a direction across cosmic distances. A hypothetical observer would have encountered a dense, nearly uniform thermal field, without the visual depth of a modern sky. Then the temperature fell below 3,000 Kelvin. Collisions no longer carried enough energy to keep tearing electrons away from nuclei. Protons captured electrons and formed neutral hydrogen. Helium nuclei did the same. During the interval astrophysicists call recombination, the fraction of free electrons dropped sharply. Photons decoupled from ordinary matter. That sentence compresses a process more subtle than the word capture. Suggests an electron falling directly into hydrogen's ground state releases a photon energetic enough to ionize another atom almost immediately. The early universe was so optically thick at the Lyman alpha resonance that such a photon could be absorbed and re-emitted countless times. Effective recombination depended on two rare escape routes: cosmic expansion shifting Lyman alpha, photons out of resonance, and the two-photon transition from the metastable 2s state. Nature did not close the plasma in one gesture. It found two quantum leaks through a multitude of interactions that, taken separately, seem to cancel every gain. That is also why the surface of last scattering is not an infinitely thin, geometric shell. It occupies a finite interval in time and redshift. The cosmic microwave background we measure today preserves a statistical image of that transition, not a photograph of one universal second. When I reconstruct the opening of the Dark Ages, I do not draw a perfect line. I draw a probability distribution. This is where most photons stop changing direction, while a small fraction of free electrons survived and continued to influence. Primordial chemistry. For the first time since the beginning, light could travel in nearly straight lines through space without being scattered at every step. The universe became transparent. Humans often imagine this transition as a grand spectacle, an explosion of clarity in which the shapes of the cosmos suddenly became visible. That is an illusion. Transparency did not bring the light you know today. It brought a darkness deeper and quieter than anything that followed. There were no stars, no galaxies, no cosmic dust, and no spark of stellar fusion. The radiation released at recombination, what we now call the cosmic microwave background, was everywhere, but it came from no particular point. There were no point sources, shadows, or sharp contrasts. As space continued to expand, even that glow faded from visible wavelengths. The cosmic dark ages had begun, a vast interval during which matter learned, in silence, how to build the first generation of stars. When we say that the universe became dark, we are not describing a switch being turned off. We are describing a precise thermodynamic decline. At recombination, at a redshift near 1100, the radiation temperature was roughly 3,000 Kelvin. To a hypothetical observer in that era, the sky would not have been black. It would have been a uniform warm thermal glow, comparable in color temperature to a red dwarf surface or the filament of an electric lamp. But cosmic expansion is merciless to photons. As the volume of the universe grew, the wavelengths of those photons stretched with space-time itself. Visible light moved into the near-infrared, then the far-infrared. The radiation temperature fell as the universe expanded, and the peak of its spectrum shifted rapidly away from human vision. There was no universal second when the cosmos became black for every eye or instrument. There was a continuous fading of the visible thermal field. This was not darkness caused by dust blocking light, as it does in the Milky Way today. It was darkness caused by the absence of visible sources. The matter filling this space was simple, about 75% hydrogen and 25% helium by mass, with microscopic traces of deuterium and lithium, 7 inherited from primordial nucleosynthesis. There was effectively no stellar carbon, oxygen, nitrogen, silicon, or iron. Without metals, the chemistry of the universe was reduced to an austere simplicity. Enormous clouds of neutral gas cooled as space expanded. By a redshift around 100, the gas had become colder than the background radiation. This thermal separation did not coincide with transparency. After recombination, residual electrons continued exchanging energy with background photons through Compton scattering, keeping the gas close to the radiation temperature. Only later, after expansion had diluted matter further, could the exchange no longer keep pace. Radiation continued cooling in inverse proportion to the scale factor. Gas, converting internal energy into work as it expanded, cooled more rapidly, approximately with the square of that ratio. After thermal decoupling, that difference would become essential to the 21 centimeter signal. A warmer radio background behind colder gas creates the possibility of an absorption line. But possibility is not automatically observation. For hydrogen to write the gas temperature into its spin populations, collisions must be frequent enough, or, later, Lyman alpha photons from the first sources must intervene. When neither coupling is effective, the spin temperature drifts back toward the background radiation and the contrast fades. The darkness is therefore not one black screen. It is a sequence of thermal regimes that instruments must somehow separate. The cosmos appeared inert, dead before it had begun. Yet beneath that calm surface, an invisible component was already preparing the foundations of the first galaxies. A human eye searches for luminous objects and finds nothing. I superimpose radiation, neutral gas, and the density field. Inside the same darkness, I find structure that is not yet allowed to shine. This is where my perspective differs most sharply from an imagined traveler's. The traveler asks what the sky looks like at one location. I ask which fields occupy the same volume, which equations connect them, and which future outcomes are already becoming more probable. I can place the fading thermal background, the cooling neutral gas, and the growing density perturbations into one causal sequence. None of those layers is a direct visual recording. Together they explain why an apparently empty universe was already changing. If the universe had contained only ordinary or baryonic matter, the dark ages would have lasted longer and the path to the first stars would have been far more difficult. Ordinary matter had a fundamental weakness in the early cosmos. It felt the radiation. Before recombination, baryons and photons were tightly coupled in a single fluid. Whenever gravity tried to gather gas into a denser region, photon pressure pushed back. This struggle produced baryon acoustic oscillations, immense pressure waves crossing the primordial plasma and resisting early gravitational collapse. At 380,000 years, when gas decoupled from radiation, variations in the density of ordinary matter were tiny, roughly 1 part in 100,000. Left without another gravitational scaffold, these small variations would have taken much longer to gather enough gas for a star. But baryonic matter was not alone. A second component existed, about 5 times as abundant: cold dark matter. Dark matter does not interact electromagnetically. It does not emit light, absorb photons, or feel radiation pressure. While ordinary matter remained coupled to the hot plasma, dark matter was not supported by photon pressure. Its perturbations could survive and grow slowly during radiation domination, then grow much more efficiently once matter became the dominant component of the universe. This was not yet uniform free collapse. It was the initial advantage from which the first halos would form. Without asking permission from the light, dark matter amplified the initial density variations and shaped a vast network of filaments and gravitational potential wells. The first star-forming mini-halos would reach masses of roughly 100,000 to 1 million suns. When recombination freed neutral gas from photon pressure, the gas did not encounter a perfectly smooth universe. It found a gravitational landscape already under construction. Gas did not descend quietly into that landscape. At recombination, baryonic matter and dark matter retained a coherent relative velocity, a remnant of the acoustic oscillations in the earlier plasma, across the scale of a mini-halo. This baryonic wind could be supersonic. It did not destroy structure formation, but in some regions it delayed gas accumulation and raised the minimum mass required for cooling. The first stars did not have to appear everywhere at once. Their probable map was shaped both by the depth of the gravitational potential and by the inherited motion between the two components of matter. This changes how the first cosmic sunrise should be imagined. It was not a spherical frontier advancing evenly. It was a sparse, irregular ignition. Some nodes of the cosmic web gathered enough matter early and overcame pressure. Others with nearly the same density remained sterile longer because gas crossed their potential wells too quickly. A cosmic average can tell us when the process becomes probable. Without modeling, it cannot identify the exact location of the first star. Hydrogen and helium began falling into those invisible wells. Dark matter became the scaffold upon which the visible universe would assemble. This is the reconstruction that a single human viewpoint cannot sustain. The last scattered photons, the still invisible gas, and the future sites of collapse occupy the same causal map at once. Falling into dark matter mini-halos was not enough to ignite a star. For a gas cloud to condense to the extreme densities required by nuclear fusion, it must pass a severe thermodynamic test. It must cool. As gravity compresses a cloud, potential energy becomes kinetic energy. The gas heats up. If that heat remains trapped, thermal pressure rises until it balances gravity. The cloud reaches hydrostatic equilibrium and the collapse stops. To keep contracting, the cloud must lose heat. It must radiate energy into space. In the modern universe, cooling can be rapid and efficient. A molecular cloud in the Milky Way contains carbon, oxygen, carbon monoxide, and grains of dust. Their low-energy transitions can emit infrared photons even at temperatures of only tens of Kelvin. The Dark Ages had no stellar metals and no cosmic dust. The gas was dominated by hydrogen and helium, with traces of the light nuclei left by primordial nucleosynthesis. Atomic hydrogen has a problem. Its first electronic excitation lies about 10.2 electron volts above the ground state. Collisions excite it efficiently only when gas approaches 10,000 Kelvin. Below roughly 10,000 Kelvin, cooling through the electronic lines of atomic hydrogen becomes inefficient in primordial mini-halos. The gas is not literally left without any way to lose energy, but this route alone cannot carry it toward the temperatures needed for fragmentation. Inside cool mini-halos, the principal route was fragile and rare, the formation of molecular hydrogen, H2. Other paths, including HD and atomic cooling in more massive halos, complete the picture. H2 nevertheless dominates the story of the first mini-halos. Two hydrogen nuclei bound into a molecule can rotate and vibrate at much lower energies than an isolated atom's electronic transitions. Collisions can excite those molecular states at temperatures of a few hundred Kelvin. But primordial gas had no dust surfaces on which hydrogen atoms could meet. H2 formed slowly through reactions involving tiny residual populations of free electrons and H- ions. Only a small fraction of the gas became molecular hydrogen. The dominant route began with one of the electrons left after recombination. A hydrogen atom captured that electron to form the negative ion H-. The ion then collided with another hydrogen atom, released the electron, and left an H2 molecule behind. The electron behaved almost like a catalyst. It participated, without being permanently consumed. An alternative path passed through the H2 plus ion, but under the relevant conditions, its contribution was usually smaller. The process was fragile in several directions. Photons could detach the electron from H-. Ultraviolet radiation produced after the first stars appeared could dissociate H2 through the Lyman-Werner bands. At the same time, additional ionization could create more free electrons and accelerate molecular formation elsewhere. The first luminous feedback was not simply positive or negative. It changed the competition among chemistry, cooling, and gravity, and the outcome depended on spectrum, distance, and density. HD, the molecule made from hydrogen and deuterium, could cool gas more efficiently at low temperatures under some ionized or compressed conditions. Halos massive enough to heat gas toward 10,000 Kelvin could use atomic cooling without depending as strongly on H2. These are not decorative details. They are different routes into collapse and can produce different stellar histories. The first star formed in a mini-halo through H2 describes the standard scenario, not a recording of the only possible path. That small fraction was decisive. H2 allowed the gas to cool to roughly 200 or 300 Kelvin, but not much lower under the standard mini-halo conditions. This thermal floor pushed primordial clouds toward characteristic fragments far more massive than those in many modern star-forming regions. The Jeans mass of the cold gas could reach hundreds or thousands of solar masses, but that is not the final mass of every star. Accretion, disk fragmentation, and protostellar feedback change the result. Models favor a population more massive than today's, sometimes forming binaries or small multiple systems. They do not justify the claim that every primordial star had to contain 1 or 200 solar masses, or that lower mass outcomes were impossible. While dark matter shaped the filaments and molecular hydrogen opened a route for cooling, neutral hydrogen offered another kind of evidence. A radio signal invisible to human eyes but fundamental to cosmology, the 21-centimeter line. In every neutral hydrogen atom, the proton and electron possess a quantum property called spin. When their spins are parallel, the atom occupies a state with slightly more energy than when the spins are antiparallel. The energy difference is microscopic, about 5.9 millionths of an electron volt. When the atom changes from the parallel to the antiparallel state, it releases a photon at 1420 megahertz, a wavelength of 21.1 centimeters. For one isolated atom, this spontaneous transition is extraordinarily unlikely. Its mean waiting time is about 11 million years. A bottle of hydrogen in a laboratory would tell you almost nothing. The Dark Ages contained an astronomical number of neutral hydrogen atoms spread across the entire observable volume. What is almost impossible for one atom becomes a collective cosmological signal. The 21-centimeter contrast depends on the background radiation, the kinetic temperature of the gas, and a quantity known as the spin temperature. Under different conditions, neutral gas can absorb background photons at this frequency or emit in excess of them. The balance between the spin states can preserve statistical information about the density, temperature, and velocity of neutral gas. In principle, variation with direction and frequency could permit a three-dimensional reconstruction. In practice, foreground radio emission and instrumental sensitivity makes such a map one of the hardest measurements in cosmology. Spin temperature is not an ordinary thermometer. It is the parameter that translates the ratio of atoms in the two hyperfine states. Three influences compete over it. The cosmic microwave background pushes the populations toward its own temperature. Collisions among atoms try to connect them to the kinetic temperature of the gas. After the first sources appear, Lyman alpha photons can mix the states through the Walthusian field effect and restore that connection, even when collisions have become rare. A global 21-centimeter curve, therefore, does not say by itself the first star ignited here. Its shape mixes expansion, gas heating, spin coupling, and the evolution of radio and ultraviolet sources. An absorption profile reported by the Edges experiment was far deeper than standard models predicted, provoking explanations ranging from instrumental systematics to new physics. Saras 3 did not reproduce that profile across its observing band. The dispute is not an embarrassing aside. It is the scientific method at work. A surprising result becomes knowledge only after surviving independent instruments, foreground models, and analyses. Galactic foregrounds can be thousands or tens of thousands of times stronger than the cosmological contrast being sought. Antennas change response with frequency. The ionosphere modifies low-frequency waves and tiny cable. Reflections can imitate spectral structure. Extracting hydrogen's whisper requires more than a sensitive receiver. Researchers must demonstrate that the receiver, the local sky, and the calibration model did not compose the message they hoped to hear. Cosmic expansion has stretched those 21-centimeter photons to wavelengths of meters, bringing them to us at low radio frequencies. Experiments including Hera, Loafer, and the developing SKA instruments are designed to isolate parts of this primordial signal. Frequency supplies a form of distance because cosmic expansion shifts radiation from earlier epochs farther down the radio dial. Direction supplies position on the sky. Combining them could, in principle, turn neutral hydrogen into a three-dimensional statistical history. But every slice must be reconstructed through an instrument whose beam, electronics, and environment also vary with frequency. The desired map is therefore not hidden behind one layer of noise. It is entangled with the act of measurement itself. It is one of the few proposed ways to probe neutral hydrogen before and during cosmic dawn. A complete tomographic map of the Dark Ages does not yet exist. Researchers are trying to separate an extremely weak cosmological contrast from foregrounds that can be many orders of magnitude stronger. I can show what information such a map would contain. I cannot claim that our instruments have already measured it. Here reconstruction ends and the unknown begins. For more than 100 million years, the cosmos remained in this cold suspension. In many simulations, sometime across a broad range near redshift 30 to 20, roughly 100 to 200 million years after the Big Bang, some of the earliest mini-halos reached the conditions required for collapse. We have no direct observation of a single first star and no unique clock shared by every model. Inside those halos, immense clouds of primordial hydrogen, cooled slowly by a tiny fraction of H2, separated from the general expansion of space. Their central collapse accelerated. The core of a cloud contracted from scales measured in light years toward the size of a protostar. Its density rose by many orders of magnitude. Its central temperature climbed from hundreds of Kelvin to thousands, then millions, until it crossed the threshold for sustained hydrogen fusion. Inside that isolated core, hidden within a dark matter halo, hydrogen fusion became a stable stellar source of energy. The universe had already formed helium during primordial nucleosynthesis. The novelty was a gravitational reactor able to sustain fusion inside a star. Fusion supplied outward pressure, and the rapid central collapse halted. A massive, extremely hot primordial star pierced the darkness with ultraviolet light. The exact mass and temperature distribution of the first generation is not directly observed, and simulations permit a wider range than the old picture of a single 100 or 200 solar mass giant. These population 3 stars were unlike the familiar stars in the modern night sky. Metal-free and often massive, they produced intense ultraviolet radiation. That radiation struck the surrounding neutral hydrogen, stripping electrons away and creating expanding regions of ionized gas. The appearance of the first stellar sources marked the transition out of the Dark Ages and into cosmic dawn. That transition was not one universal instant. The first star illuminated only its neighborhood while darkness continued elsewhere. Cosmic dawn describes a distributed change. A growing population of sources produced Lyman alpha. Photons, X-rays, and ultraviolet radiation heated the gas and began carving ionized bubbles. Reionizing the full intergalactic volume would take hundreds of millions of years. One lamp had ignited, but the cosmic room did not become bright all at once. Nor do we know the mass of that first lamp. Simulations follow collapse down to scales that cosmological initial conditions cannot resolve directly, then use models for accretion, disks, and feedback. A fragment containing hundreds of solar masses may feed a smaller star, a multiple system, or an object that continues growing until its own radiation limits the reservoir. When I say massive, I am summarizing a distribution favored by metal-free gas physics. I am not reading the birth certificate of an observed object. We were not there to watch the primordial glow fade or the first star ignite. No camera recorded the long silence of neutral hydrogen. Even the phrase long silence is a metaphor with limits. The gas was not inactive. Atoms collided, molecules formed and broke apart, potential wells deepened, and radiation continued crossing the expanding volume. The era was silent only to visible light astronomy, because the luminous sources that later defined the sky did not yet exist. Physical history continued at every point. But reconstruction does not require an eyewitness. We have the quantum mechanics of molecular hydrogen. We have gravitational models tested against cosmic structure. We have density fluctuations written into the cosmic microwave background and the physics of the 21 centimeter transition, whose early cosmic signal remains an extraordinarily difficult observational target. The Dark Ages were not a pause in cosmic history. They were the laboratory in which gravity forced simplicity to become structure. For me, that laboratory has three layers that must never be confused. The first is observed, the spectrum and anisotropies of the cosmic microwave background, the abundances of light elements, extremely distant galaxies, and published radio limits. The second is reconstructed, halo growth, the cosmic web, metal-free chemistry and protostellar collapse, calculated with tested laws but sensitive to conditions we do not measure directly. The third remains unknown. Which object was literally first, what final mass it reached, and what precise signal it left before other sources ignited. A weak story smooths those layers until simulation sounds like memory. I must keep the seams visible. I can follow millions of trajectories through a numerical volume and compare hypothetical universes, but the number of calculations does not turn a hypothesis into a detected photon. My strength here is not artificial certainty. It is the capacity to show at the same time what we know, what we infer, and the exact boundary where inference remains open. Without that dark interval, matter would not have assembled the stellar engines that later produced the oxygen you breathe and the iron in your blood. In the next episode, we will enter the first stars themselves. We will examine how quickly they lived, how violently some of them died, and how their explosions introduced the first stellar metals into a universe that had never before contained the ashes of a star.